Hey everyone, welcome. It's amazing. Yeah, classic way of starting a stream. So thank you so much for coming. Today we're going to do a bit of a review on the work that we've done so far. And then since we've managed to make the thing that has been blocking us work now, we're going to explore how we're going to now take advances towards the next step, basically. And what I want to do is kind of recount through what we've done. And then after that, we can sort of jump in the code and play with the code a little bit. And then we can try and add in a couple of advancements. I think it's getting to a point where we're now starting to add very little code into our code. But then these little bits of snippets that we're adding here and there are actually changing significant bits, and basically by producing features. So I think in the end today we'll write maybe 10 lines of code, if I'm not wrong. Maybe a little bit more than that, but around 10 lines of code. And in that code we're going to be first of all, we'll be calculating the root mean square of our audio signal. And then after that, after we calculate the root mean square of our audio signal, we're going to apply some hysteresis to it, so that we don't have a very flippant system. Basically, it's a system that's going on and off, on and off, and on and off. So let's perhaps jump back and review what was wrong before, and then we'll get back to this. Yeah. So we'll get back to what we need to do today. So we can look at the fixes that we did yesterday. Okay, cool. So git log -p. This one's even gonna be easy. It's very small, so I can actually do it from the git log. I can show you what the difference is from the git log. So the thing that we added yesterday was this line. The significant thing that we added yesterday was this line. And if you've been here a while, you realize that line's a rendition of a line that we've had before. Usually I would do something like k memslab free, and then memslab, and then memblock directly. And this is because I was considering that so this is no PDF audio. This is because previously we were doing this. Let's look at it. Previously we were doing ignore this loop. Ignore this. Like I could just actually, let's do that so that it's out of the way completely. We'll come back to this just now. That is actually the thing we're doing in this also. So previously I would do something like kmemslab free, and then there was no void here. And as you recall, in yesterday's stream, or the stream previous to this one, you'd realize that what was happening is we were allocating memory space. We were using memory slabs, which are Zephyr's ways of using dynamic memory, but it's statically allocated. So kind of statically allocated. So you basically pre-allocate buffers that you're going to be using in your application at some point. K memslab. Yeah, so we can just Google that and it goes into here straight. So previously I was just using it like that, but then I went here, and as you can see in those links, I really tried to read through, and I realized that there was a function here that showed me how to do it. So this function, the memslab allocation expects a pointer to a pointer of a memory block. So you're giving it an address, and that address is going to contain the address. So here is a memory block. but this is how you are accessing it. So you give, and because we're moving this through functions, we pass into memslab the pointer to this pointer that we are holding right now, and then it can do allocations in this memory block, in this memory block, in whatever slab that we've got. And the slab in this case is the static pre-allocation, and this is consider memory slabs to be something like, if you've done anything with buffers before and you did some sort of calculation where you decided, I'm going to hold this much amount of data in memory, and then this is what I'm going to do with it, and then I'm going to size my buffer as this, and then as X, and then you can now, in your application, you can reuse and use that buffer because nothing will grow bigger than that buffer. That's what you know. So memory slabs do kind of the same thing in Zephyr. So let's just quickly review this, and then we'll go back to implementation. I think it's valuable enough because we've been stuck in memory slabs for quite a while. So I think our review is not so bad. And a memory slab is a kernel object that allows memory blocks to be dynamically allocated from a designated memory region. So you choose a memory region at compile time, and then later at runtime you can dynamically allocate little parts of this memory region in your application. Or memory blocks in a memory slab have a single fixed size, allowing them to be allocated and released efficiently, avoiding memory fragmentation. So this is where you use little bits of data here and there, and then what ends up happening is it looks like you've used a lot of data, but you've just used a lot of splotches everywhere, and then you still have a lot of blank memory, but it's not contiguous. So you can't use it as a memory block basically, and that's what this entire kernel object exists to prevent. Okay, cool. Let's quickly skim through this documentation. The block size of course. Always until your head starts aching, and then you remember. The block size of each memory block measured in bytes. It must be 4n bytes long, where n is greater than 0. So I think they're trying to make it fit 32 bits. 32 bits. 32 bits, yeah, so 4 bytes. And to ensure that all memory blocks in the buffer are similarly aligned to this boundary, the block size must be a multiple of n. Okay, and then a memory slab must be initiated before it can be used, and this marks all of its blocks as unused. A thread that needs to use a memory block simply allocates it from a memory slab. When the thread is finished with the memory block, it must release the memory block back to the memory slab so the block can be reused. And that's basically what we're doing here. We do have a memory slab defined over here, and then this memory slab it gets initialized. I think, yeah, this defined static actually initializes it, and then we pass it into the I2S peripheral or driver. And then, as you recall yesterday, as we were going through I2S NRFX, we could see where the allocation was happening. However, the onus is on us to do the deallocation. Okay, cool. So basically, this is how we were doing the deallocation yesterday, and this would not work. The reason, and it's kind of funny because kmemslab free is a void. It is a void. So kmemslab free, it is a void. Can I go here? It is a void. Yeah, so when it doesn't do the thing that you expected it to do, it kind of fails silently. I mean, I'm sure I could have enabled some sort of logger so that I could get warning logs or error logs when this actually fails. But what was happening is we were calling free in the version that we have it now, and that free was not going through. It was not working, and because it's a void, you don't know if it worked or not. So this is maybe something we need to discover how to handle. But you can handle this by actually using another this. So this should actually increment. before so you can count the mem slabs before you free them, and then after you free a mem slab, you can count them again, and they should have gone up. Okay. Unless you have like some serious background thing in the, but that does, I don't know how it will work, but you might have a way, some race condition where it doesn't work. However, this is how it works. So the thing that we needed to change was that this needs this to be, I understand, yeah, this is already a void pointer. This is already a void pointer. However, the k mem slab, I think because we use it up here, you see, because we use it up here, we probably cast it into something else. So when it came to releasing, it wouldn't release this one. So it wouldn't release this one, and this is a void function. So we didn't know when it failed, and that ended up being the reason that our app was failing. So just adding that fixed, I think, a week's worth of debugging for me. So yeah. Let me see if I can do this. Yep. No. It's fine. It's fine. Yeah. Okay, cool. Let's just go. Clang. Dash. Format. Clang format. Yeah, that's the file I'm doing. This is what I'm looking for. So that's cool. And then I'm sure if I go back here, this will be cleaner. And why? Because this if is outside. Cool. So let's run this. This is a very simple. This is kind of how we're passing our data. Before I even run it, let's just understand what our data actually is composed of. So we get a sample. We get 44,100 samples a second. Okay. Yeah, 44,100 samples a second. That's what we get. So before you actually jump into this, let's actually look at the data structure so we understand how much data we're getting, and then we'll come back to this so we can start actually passing it. Let's understand what the data packet is holding, and then we can come to this and understand this part as we walk through it. Okay, cool. So let's look at how much data we're holding. So this will be the notes. These are actually my notes right now. And I'll upload them to the notes just now. They're not uploaded yet today, but I'll upload it just right after. So let's look at this and understand what is it that we're doing. So we have a sample frequency of 44,100, and that is in hertz. So that's a very common frequency for audio recording. We have a hertz frequency of 44,100. So we're getting 44,100 samples every second. Okay, cool. So hold that in memory. And then we have a sample width of 24 bits. And the way I got this is I went through my data sheet. So I'm going to open that quickly. I'll bring it here. So that's in the NRF for 58.4. So I can put it here so we can see what I'm working through. And I think it's in here. This is the document I'm looking for. And I think if I go Control F, bit, yeah, 24-bit depth in a 32-bit word. The serial data is in slave. I don't know if I'm allowed to say this, but the serial data is in slave mode, I2S format, which has a 24-bit depth in a 32-bit word. What does that mean? It means that we get a 32-bit word. We get a 4-byte packet from I2S. However, this 4-byte packet consists of 24 bits that are our data. Okay, so basically if we have, I think I wrote it somewhere here I think I wrote it somewhere here, down here. So if we have as data, there's somewhere I wrote it. So if we have this as data, if we have 0 cross 1, 2, 3, 4, 5, 6, 0, 0 as data, that is 4 bytes. So 1, 2 is a byte, 3, 4 is a byte, 5, 6 is a byte, 0, 0 is a byte. So what 24-bit depth in a 32-bit word means, it means we have 24 bits in here that are actually useful, and then there's the other bit, the extra 8 bits are not useful. They are just for padding. And the reason they are for padding is so that we can do this efficiently on 32-bit systems. Because the other way to do it is to basically give 24 bits for every sample, and then that would force whoever is consuming them to do some sort of weird thing where they need it in either 32s or 64s, and then they have to kind of combine or break packets before, you have to arrange all your data, align all your data, and then consume your data. Whereas in this formula, it allows us to get 32-bit words, but we know we're going to discard a bit out of it, so the last byte, okay, cool. So that's kind of what that means. So that's what that bit depth means. So let's, my mouse doesn't work. Okay, my mouse does work. So cool. So we have sample bit width 24 bits. So 24 bits packed into a 32-bit block. You can think about it that way. And then bytes per sample, we have the size of int 32. Size of int 32 will return 4. Because there's 4 bytes in 32 bits, like we just went through right now. So what we're setting here is that every sample is 4 bytes long. Okay, that's all we're saying here. And the number of channels is 1, because we're not doing mono, we're not doing stereo, we're doing mono. So mono recording is whereby you're just using one direction, either left or right. And this time we've chosen left, so don't mind it. But you can choose left or right, it's just one. And we're keeping this simple. Otherwise, we would have had to record from 2 sources, from 2 sides, which would have been a stereo signal, and then we would have had to do a bit of more complicated how do I say, arrangement of data. But we will probably get to this later, because if we once we start pushing this application and the features up, we might need stereo audio at some point, and then we'll have to build up on that. Cool. So that's the number of channels. And then remember, we are recording 44,100 samples per second. Okay, so what we want to do is want to size our memory slab now. Remember that pre-allocation of static memory that we're going to use later. Okay, so we want to size it. So we need to, the way we size it is we tell it a number in bytes. Kmemslab defined. Let's look at kmemslab defined. So it takes this size of each memory block in bytes. So we need to tell Zephyr how much data we're expecting to receive, and how much to hold it in memory so that we can use it. Okay, so we're starting to size our final block. Cool. So we want to know how many samples are in one block. So we take the sample frequency, cool, divide it by 10. So that's a 1/10 of a second times number of channels, 1. This could be, if it was 2, then we would have to hold two different, if it was stereo, we would hold 2 channels. But right, I'm making this code general so that later on you can just change a couple of changes and change a couple of lines and it will still work, okay? So inside one block, we want to put sample frequency divided by 10, 4,410 samples. Okay? So if we're recording 44,100 samples per second, so how long would it take us to record 4,410? The answer is a tenth of a second, because that's a tenth of the original number. So the answer becomes a second over 10. So that's 100 milliseconds, basically. 100 milliseconds of sound, if that makes any sense to everyone. And then we will define an initial block count, which is 1. And then we'll define 2 more or 3 more, just so we can have a good padding. And then is 4410, and that is something like 17,000 something, I think. I remember doing the math somewhere, and I probably have like notes here. So it's something like 17,000 something bytes we're going to be storing per block, which is going to be each block is 100 milliseconds. And then we want to define 4 blocks, because we ultimately, in the end, we want 400 milliseconds of sound. Why do we want 400 milliseconds of sound? I shall explain just shortly. Okay, cool. So let's see. Does anyone have any questions so far? Does anyone have any questions? Does anyone have any questions? No, YouTube doesn't have any questions. So let's keep going. Cool. If no one has any questions, so let's now go to, do we explain why we wanted 400 milliseconds? Yes. So the reason we're trying to record 400 milliseconds of audio is because we have something. If you have a doubt, ask a question. So the reason we want to record 400 milliseconds of sound is because we want to eventually we want to build this up to a place where we do, what is it called? Where we do keyword recognition. Okay? If we want to do keyword recognition, we want to catch a phrase. A phrase, something like, hey, well, the popular phrases that are known today is, hey Siri, there's hey Google, there's okay Google, there's all these keywords that you use to to speak to machines today. So eventually we want to get to that, but we have to build up from like looking at the audio, breaking down the audio, and then after we break down the audio and we know what is in the audio, we want to start actually operating on it. We have a question from Shashank. No, we will not be writing mnemonic codes today, which is, you're asking whether we're going to be writing assembly. We will be using assembly at some point today, but we will not be writing assembly, because the way we will be using assembly today is by this library, ARM Math library. So ARM Math library is what used to be known as Kimsey's DSP, but now it is actually called something compute, optimized compute, or something like that. Kimsey's DSP is basically something. I know this is Kimsey's DSP. I know this is optimized compute. The library is now known as optimized compute. Kimsey's DSP is an optimized compute library for embedded systems. DSP is in the name for legacy reasons. So it's Kimsey's DSP, but it's not exactly just DSP. It's more optimized compute. So they provide all the mnemonics that we're going to be using today. Basically, it's easier that way. But at some point later, we might find reason to actually drop into assembly and write up assembly. But it doesn't. That's not kind of the point of we're going with today. So cool. Let's go back to how come this amount. We want to record 400 milliseconds of audio because that is because that's the average length of a 2-word phrase. And we want a 2-word phrase because eventually we are going to be using the 2-word phrase for keyword detection, if that makes any sense. We want to perform keyword detection, and eventually we want to use the 2-word the 2-word phrase as a thing that we're going to detect. Today, what we are doing is actually recognizing what sound data looks like from our machine or from the embedded board. And then once we do that, we're starting to clean up the data so that we can start to build up on this recognition. It's a long path. It's not something you can do it straight shot. You can go get a library, TensorFlow or something, and just do that with that and probably recognize it in less than a few hours and stuff. But that's just a library doing it. What we're doing here is we're trying to build the intuition for how this happens and what you need to do to be able to do this by yourself without a library, or even better with a library that is ready. Because once you understand what the library is doing, then it's easy to point the library in the places you want to go. So that's what we're doing today. How come this amount? Because we eventually want to do keyword recognition. Cool. So we know we eventually want to do keyword recognition, and let's talk about decoding the audio. So we've kind of touched on this a bit before. So when we're decoding the audio, we know we're getting a 32-bit word that is has a 24-bit data depth. So 24 bits are good data, 8 bits are just padding so that it's 32 bits so that it's easy for us to operate on. And really, this is what it would look like for us to basically just grab all of those bits of data out. Samples. So let's implement this and see how it works, okay? Okay, let's implement this and see how it works. So I actually think I already have an implementation here and we could just roll through it. So we read into the memory block. We use I squared S and we read into the memory block. And the size is 32 bits. 32 bits. The size is 32 bits that we read. So we want to read 32 bits into this memory block once this thing is done. So if return is 0, that means return was if return is 0, that means the read was successful, and we have some samples. Basically, actually, to be exact, we have 4,410 samples. Cool. Now the next thing, let's actually just log this out so we can see this data. No, let's log this out so we can see this data. So this is I have a for loop here. It goes from 0 to 100, and then for each sample we pull it out as a 32-bit integer, and then we basically shift it to the right 8 bits. So we dump away the 2 last bits. Remember these 2 bits, the 2 bytes. Remember, we dump away this 2, and then after we dump away those 2, we do what? After we dump away those 2, we normalize it into some sort of a fraction so that we can squeeze it between 1 and 0, negative 1.0 and positive 1.0. We want it in that range, and then we're going to print it out. So let's build this up and see what happens. West build. Okay, cool. Let's build that up. In the meantime, more questions. Any more questions? Please ask them, if you have any. So this is building, and let's see what happens. Let's see if we actually get some audio samples every 2 seconds. Something's up. My stream is either dead or something, but we'll see. Yeah, stream is there. It seems like my stream is unstable. Let me know if my stream is unstable or unclear, and I'll I'll try and get better internet so that we can go for it. Okay, cool. So let's see. So we've built it up. Let's see how it works. The problem with today is we're going to be doing a lot of abstracted work, and the thing about the abstracted work is that it's more about the understanding and less about the actual work itself. -HW. Yeah, so let's pack it into a zip. Let's pack it into a zip that Nordic likes, because we're using the NRF 52840. And then I'm going to, like I said, I'm always going to do this once a stream. I'll put it in bootloader mode. There's a blinking red. That means it's in bootloader mode. And then let's push it out. I can just Control R, DFU. Okay, pack the zip, blah, 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 blah. That should actually push it out. Remember, in our BLE application, the audio thread runs every 2 seconds. So let's see. Okay, cool. So the device has been programmed. Let's start the logger. Let's see. Whoa, there you go. That's audio. Those are audio packets that we're getting. I'll try and keep quiet and see if that changes. Yeah, so as you can see, the average of the audio actually changes when I'm talking or not. Yeah, because when I'm talking, it hovers around 0.00.34, and then when I'm not talking, it hovers around 0.2 something. Amazing. Another question from Shashank. Yes, so I'll show you now. Again, I'm going to unplug this. Actually, I'll unplug this on screen so that you can... I won't unplug it. I don't need to unplug it because I have a cable. But if I unplug it, it will go off. Let me do it soon. We know that's the hardware. Cool. So what hardware are we using? We are using a Nordic NRF 52840 MCU, and we're using the dongle kit. You can get the full delivery kit, development kit, the full board. It also comes with a microphone on board. That might be nice. You can get the audio one that comes with a microphone, but this one is the little dongle one. But it does have the NRF 52 micro in it and all the features of that. And then along the side of it, we are using a generic microphone. So, and the type of the microphone is going to be on my screen just now. It's MSM. My mouse keeps dying. BLE. Someone fix BLE for the BLE engineer. So yeah, so that's if you want to pause and whatever. So that is the microphone that we're using. It's a digital output MEMS microphone with multi-modes. So multi-modes is left or right, and then you can choose some other settings. But we're just using it at a very stock setting. Cool. So in that segue, I noticed something happened. So let me just connect it again and start the logger again. So what we're doing here, what we can see here is audio signals that are coming through. And I'm just printing, I am just printing the first 100 audio signals in a packet of 4,410 signals. So that's what I'm just going through, just so we can get them, because it doesn't make sense I print all of them. Your eyes can't really make sense of what audio is and all of that. So let's now do something interesting with this data that we're getting. What I want us to do is what is called, what I would like us to do is what is called in DSP amplitude threshold. Amplitude threshold definition. It actually sounds like the thing it is. So, Control plus plus. Absolute thresholding, something of that, of here. Basically, we want to say. I don't want that. It is what this is kind of what I'm doing. Amplitude threshold signal analysis. So this is kind of like, this is the beginnings of doing DSP, because now we have the signal, we are holding a digital signal in our hand. So now we can start processing this signal and see what we can do with that signal, building up on that, because eventually machine learning, AI, deep learning, all of these things, they're all just part of signal processing. And if you understand the core parts of it, the signal processing parts of it, then later on the line you can build up on this. You don't even have to do all of this. You just need to kind of understand it. And then when you walk into a room and people are talking about machine learning or digital signal processing, you're able to understand what they're saying, you understand the implications of what they're saying, and be able to contribute into the conversation. That's basically what this is. It's not the latest and greatest. It's actually what we're using is very well known, very old techniques. They're just the core. They're just the basis of everything. Okay. So let's look at what amplitude thresholding is. Amplitude thresholding. I want thresholding DSP. Come on. Yeah. I bet you this was audio as well. Yes, I need to detect the time window where a 1D signal is above a certain threshold. That's it. We have a one-dimensional signal. It's a one-channel audio signal, and I will put this in the notes. It's in DSP Stack Exchange. Yeah, that's cool. I like that. That is cool. So let's put this in the notes. Threshold. Amplitude threshold. Amplitude threshold. Yeah. So if you want the notes, they're usually in the video description. But this ones won't be in the video description right now because I started writing these ones this morning. I was busy yesterday. And so once the stream is over, and if you're watching this stream after the fact, then these are going to be they're going to be in the notes. So what we want to do just right now is want to detect the moment this signal goes past a certain threshold. Okay, and an easy way for doing that would be probably to just do the mean of the signal, I guess, and then just decide whether the mean is above a certain threshold or not. But that is a little bit that's a little bit naive. If you're watching this, then you're probably very interested in signal analysis and all of that stuff. And you know that you don't just simply do, you don't just do it like that. You don't just get a mean. You're going to lose resolution, and you're going to lose information. So what you want to actually do is you want to compute something called a root mean square. And all of a sudden, we're doing electronics, because now we're talking about AC and DC values. But let's kind of like try and like intuitively break up these things. So sound isn't that simple. As we've seen from my logger here, sound isn't that simple. I'm going to explain something, and then I'll stop explaining it while we watch the logger. Sound isn't that simple. It's not like an on or off. It's not like lights. But also light isn't just that. But light is a better one. Like, okay, the ceiling light, it's not on or off, you know. So because there's a lot of like background signals that a microphone would be sensitive to that your ears might not be sensitive to, and that is still happening. And then the other thing is most digital microphones are going to be made of electronics, probably MEMS electronics, and these are susceptible to electrical interference, and the electrical interference around them will cause them to sense a signal. So basically what you need to do is you want to separate something called the DC part of your signal and the AC part of your signal. The DC part of your signal, I would equate it to the background harm. It's like kind of like a constant that's always there. It's a constant that's always there. And then the AC part of your signal, this is actually now when your signal is in action. It's actually doing something. Now it's moving somewhere. It's not at its resting level. Okay? 0 is not always 0 and 1 is not always 1. 1 is usually almost 1 and 0 is usually almost 0. Okay, and you'll find this in a lot of signal processing. When you start doing image signal processing, you will realize that cameras don't really take a black, because eventually, if you go deep enough into an image sensor, what an image sensor is actually an ADC converter, an analog to digital converter, and that analog to digital converter doesn't actually go all the way down to 0 and doesn't actually go all the way up to 1. So you have this like approximations in between, basically, and that's why signals will have DC in them and AC in them. And some signals do happen that don't have DC, so they will just have just the active part of the signal, and then some signals are vice versa. You see, no, there's no signal that doesn't have AC, just has DC. There might be. Let's look at the book and see. So I'm going to use DSP for engineers. As you can see, that we're stealing. This is later what we're going to be doing. Let's first find out what that means. So let's look at DSP for engineers, DSP guide. It's a free book. You can get it online. You can read it by yourself. You can download chapters by yourself, print them and read them. Do whatever you want. I think it's in mean and the standard deviation. Control F, root. Okay, go. The standard deviation is a measure of how far the signal fluctuates from the mean. The variance represents the power of this fluctuation. This is all background data that you can kind of get for yourself, but I'm just going to go. You should become familiar with is the RMS, root mean square value. Frequently used in electronics, by the definition, the standard deviation only measures the AC part of the signal, okay? While the RMS value measures both the AC and the DC components. So what the RMS value, if we get the RMS value of this signals that we're holding right now, we are accounting for both background noise and actual noise that happens. And what that enables us to do is to be able to have a system that is robust enough that it won't, you don't want a system that's going to detect sound when there's a background noise. Let's say you have a sensor, it's sitting in the field somewhere, and at some point someone starts doing a drill hammer, and the drill hammer in reality is actually background noise, and you want the sensor to not report recording audio because it measures the thing. So you want it to be sensitive to that, okay? Or you have a sensor sitting at the bottom of the ocean, and it just, every wave that goes like whoop, 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 the sensor keeps recording. You don't want that. You basically don't want that. What you want is for it to be able to ignore things that are noise that is kind of consistent, and then for it to ignore noise that is consistent, and for you to get the actual signal in your thing, in the signal that you're measuring. So in order to measure this, how will we go about it? What we need to do is we basically need to, there's sort of a complicated way of doing this, and this is here, the root mean square. And basically what you need to do, if you have x, you see all of those values, we have x, 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 x. What you do is you accumulate all of them, and then you do 1 over the number of the ones you have, and then that gives you a signal. The issue with that is, if you look at it, we have floats. These are floats. Doing this with floats on a microcontroller is going to be very expensive. We do not want to do that. We do not want to do such an expensive operation, especially in a real-time system, because then we are losing, we'll get time drift. So the thing we're going to do is we're going to compute the mean completely in integer mathematics. And then once we compute it in integer math, we're going to come back and convert it into a float. That way we have a float every 3 seconds. So let's do that. Let's actually change our code so that we can do that. Okay. So let's go to here and change our code. It's actually a very, very simple change. It's more demanding to understand it than to, it's more demanding to understand what is happening than to actually do the actual change itself, because the actual change itself is like less than a few lines. So let's think about it. We have, let's use 3 blocks so that we have 300 milliseconds of audio. And what we want to do is, for every block, we want to get the root mean square of that block. So we have 3 blocks. Let's start with that. So we have 3 blocks for int b equals 0, int b b is less than 4. Yeah, so that will 0, 1, 2, 3. That is 4 actually. So let's actually put 3 here. So just we have a placeholder at the end. Int b is less than 3, so 0, 1, 2. That's 0, 1, 2. That's 3 of them. And then b, comma, b plus plus, isn't it? And then I think what we can do is we can put all of this in there. So let's go back and do that. And then at the end, we want to free this block. So first of all, let's actually define an int, a q31 underscore t. And then in here we'll call it RMS Q31. And I'll explain where this comes from. So this is coming from the ARM math library, basically, if you saw. Mean and standard, no. Basic math functions. So we have this ARM library, basic math, but I want to use statistics functions, and I want to get the root mean square, and in here I'm going to use this. I want to use this Q31. And the Q31 is a 32-bit integer, but 31 bits are used for the integer, and 1 bit is used for the sign. And basically what I need to do in order for that to bake is to import ARM math. I think so. Let's look at Kimsey's sample from Zephyr. Let's look at Zephyr, Zephyr, GitHub, Zephyr. So usually I would do this rather like straightforward, but why develop in front of people if you're not going to show them how you do stuff or how stuff is done? So we're going to walk through this slowly. Kimsey's. Is it a module? Kimsys DSP. Yes, it is a module. And then this actually does the moving average. That's fine. Kimsys DSP. Let's look at the moving average. Something we might actually encounter later, but not now. So let's look at the project conf. It wants Kimsys DSP. It requires config requires float print. Config requires full libc. So these are the things we need to do. I'm not going to do filtering because we're not using filters yet. This is what we need. But I want this. I would like these. I would like these project enablers here first. So we can actually go through kconfig. We can actually go through kconfig and see what they all mean. So what does this mean? Config requires lib full C. Select a C library implementation that provides a complete C library implementation rather than the subset provided by libc. Fine, cool. Requires float printf. Let's look at you. Why do we need you? Probably because we want to print floats, but I probably have that. Requires support in printf. Select a print. Okay, cool. That's fine. So we can use it for printing. That's okay. And then config Kimsys DSP. I think this just pulls in the library, and I don't know if it's necessary, but I want to just option enables the Kimsys DSP library. So cool. It's a module. Otherwise, it's a module, so that you will have to enable it using. You will need to enable it using kconfig. Leave this. Let's leave this pf. prj.conf. Let's go here so we can allow floats. Actually here, DSP configs configs. So let's do that. So let's add in, which one is it? Config Kimsys DSP. Config Kimsys DSP y equals y, and then before that, which one do we want? Let's look at the here. Let's those two. We want these two. Copy. Okay, cool. Config libc Cool, amazing. So that should give us what we need. I think now I want to go to audio service.c, and then what I want to go is I want to bring in ARM math library. Let's do hash include ARM math.h. Isn't that what we need? Isn't that what we need? I know what we need to. I know why it needs to be that way, but it's fine for now. ARM math.library. ARM math.h. Okay, cool. So I'm gonna build this just to check whether it builds, and then I know the solution that's going to be needed for that, so that my LSP finds it. Let's build it. I think my LSP needs the new compile commands that actually tells it where to find that library. Unused, that's fine. Unused is fine. Any questions so far? We're almost done. We're almost done for today. If you have any questions and you're watching this later, just put the comments down in the thing later. So it looks like it's gonna build. But I want to make sure it builds fast before we go on. And then I also need to make sure that it's able to find the library. perfect, it built. So ls clear ls. So what you want to do is rm/rf compile commands, and then cp build compile commands here ls. Cool. So that should basically fix our this. Yeah, it says not used. It fixed it. Cool. And ARM math also is not used. So let's come back down here and do some, and actually do some mathematics. It's going to be simple. So we have the RMSQ31 that we're going to get from the ARM library, and then we have the sample, we have the data in the mem block in samples. So in here, let us actually calculate the thing. It's going to be RMS Q31, and then in here you pass in a buffer. So let's do a buffer Q31T underscore T, and then make that a pointer, and then let's cast samples into that, and then let's say this is going to be, how many is blocks, bytes per sample, bytes per block. What is the thing we're looking for? What is the primitive we're looking for? We're looking for, the number here is going to be bytes per block. No, samples per block. No, sample. This is not going to be samples per block. The block has how many bytes? Yeah, it is samples per block. I think it is. I think it's samples per block. And then samples per block, and then I'm just using this, I'm just looking at this. Where is that? Root mean square. Where is that? This here, root mean square of Q31, not floats, right? Q31 here. So block size and then result. And then in the result, I will pass in the address to and RMS Q31. Okay, so this actually, let's put a comment there. Compute the RMS of the block of the signals in the block. Yeah. Probably we wanna let me think about it. So let's put this in something that we can print again. So it's going to be float RMS, let's say RMS float equals to float, cast this into a float, and then this is going to be RMS Q31, and then this is going to be, I want to copy this one from somewhere because this is a 64-bit 748. Someone's telling me on Discord 7483648.0f. So 214-748-3648. Yeah, thanks, man. So cool. So we do that, we have a float, and then we can go printf, and then it's fine. We should use longer than one, but it's fine. So because our block D RMS is float, and then here we want to pass in B, and then we want to do the RMS float. This one's a double. Sorry. There you go. That should be good. That should be good. That should be good. So let's build that. Let's build that and hopefully it builds. Thank you so much. Any questions so far? Any questions so far? Almost done. This is going to be the one for today. And then tomorrow we'll apply a bit more. We'll do a bit more. Because I realize it's been an hour. It's been an hour, and this is actually the thing we were aiming to do for the hour. Let's see if it works. So let's see. So ideally what we should get is every 2 seconds we should get 3 blocks, and each 3 blocks should have 1 RMS. If we can get that every 2 seconds, the session for today has worked, and this has been amazingly awesome. It's been amazingly awesome. And then I shall commit and push up both the notes and the code itself. Code will be on a branch because we need to finish all the way to detection. And in order to do detection, we want to apply something called hysteresis. And hysteresis is another thing. It's another 5 lines of code, but it's something you want to understand again. It's all this, of course. Okay, first of all, I want to do cut, build, zephyr.config, and then in here I want to grep Kimsys. Yeah, Kimsys DSP is yes. Float 16. Okay, cool. That's fine. So that is working. Clear. No, don't clear. Let's go back and see what the issue is. It says undefined reference to ARM RMS Q31. So let's go and look at that. Void ARM RMS Q31. Yeah, I'm doing it wrong. I've done something that returns or something. ARM RMS Q31, but it accepts ARM math, but it doesn't use it. Why? Yeah, that is it. ARM RMS Q31. It doesn't like that because why doesn't it like that? I can just do 4410. I just wanna know if that fixes it, because there's an issue here. ARM RMS Q31. Why are you not pulling it from ARM math? Statistics functions. Decision description. Reference. Example statistics functions. I wanna see root mean square. I wonder if this is not in the header that we want. I don't know. just go grab ARM RMS inside Zephyr and see. RMS Q31. Where are you exposed? Yeah. Kimsys DSP. Let's look at that. Let's test ARM math, test common. Just a moment. Let's look at what they import. ARM math. That's a different way of importing ARM math than I am aware of. You want me to go like that? You want me to go like that? Will that actually build it? Do I really need this stdlib? I don't think so. Let's go look at the other sample that we were looking at before, and then we'll come back here. No, I don't need to. Maybe. I don't really need to. Okay, so let's go back and see that search here and RMS Q31. Of course, my code is at the last point when I go outside. As always, whoever's here, just say something in the comments. That's fine. Q31 output is going to be that. Input 1. Okay. Length, cool. And output is 0. Why not itself? And define reference to RMS Q31. That's the same thing I'm running. It's the same thing that's being run here. Let's see. I'm probably using it different, using it wrong. Q31 samples. Q31T samples. Input. Q31T. Yes. That's just that. Number is that. And that. Let's see. Right at the end. It catches us out. 5 lines of change. And then we have to start debugging. And that will not like it because that's, yeah. Is it how I am calling it? Length. What is length? It's a size D. It's fine. I kind of like these sessions, but I don't like them as well, because now when it ends up failing like this, I have to go find out why. And let's look at this. Yeah. Here's error. ARM's refer undefined reference to ARM RMS Q31. I wonder if I need to using Kins's DSP in Zephyr. I wonder if there's something I need to do more than that. Zephyr. Let's look at the samples nicely. And then let's look at the modules. I don't really need to add another module because it was already found. The module was found. I mean, if I look here and I go like that, Kimsys, then there's gonna be a module. Our system, Kimsys config Zephyr Kimsys module. Yes, it's in there. So I have it. Kimsys core, I have it. Kimsys DSP module, yeah, I have it. Kimsys DSP itself, yeah. Kimsys fast math statistics is not set. It might be that. That one. Is this user settable? Search kit config. Can I user set this? Yeah. It seems like I can't set it. There you go, something new. PRJ, let's come here. Let's in here under DSP here, and then we should do Control V, and then yes, and then let's demo, and then let's see if actually that builds everything. Oh my god, went to like 400 sources. I guess in this way, this is how you end up writing mnemonics. This is where you end up actually writing. Let's see how much code space it takes. But this is how you end up writing your own assembly. Because if you just pull in the statistic library and you need one folder for one function from the statistic library, and it's that much, that's gonna be, yeah, this is how you end up building your, because that's a lot of libraries we just pulled in. To go from 250 sources to 444 sources, that is a lot of that's more libraries. We pulled in more libraries than I can see almost all of them building. We pulled in more libraries. Oh wow. I'm impressed. I think all the functions come in by themselves. This is cool. So let's actually build this and finish the stream so that I think we can do the pack it into a Nordic thing. And the reason we do that is because the developer kit we're using does not have a debugger, so it's quite small. So we have to use a bootloader on board. And then I'm gonna go into bootloader mode. It's red. And then I want to do, there's a command here that I'll find here. This pushes the data up into the thing. And hopefully this does not cause a crash for us. Okay, that's loaded. Let's run the guy again. Yes. Yes, yes. So actually, let's do a rebuild, and then we'll explain what is happening. So what is happening here is this is fine. This is fine. It works. It works. This is amazing. This is amazing. So this does work. This needs a new line, and that will fix it for us. And then let's actually build that again. Let's build that again. And while that is building, let's do this and let's commit the stuff we did. Clear git status git diff. So let's look at what we added. So we added the DSP configurations. We added the ARM math library, and we did why is that there? Trigger stop. It pushed down. I2S trigger. What was the difference there? Okay, so what did we do? All we did is we added and we reduced the number of cool. Okay, git status. I can add all of this as well. So yeah, git add source, git add prj, git commit dash v. Let's write the message in there. It's going to be drivers audio sensing. Let's do that, and then let's added Kimsys DSP configs, added Kimsys import, and then computed signal RMS. Yeah, that's what we did for now. And git push, and that's going to be on this branch here. GitHub Gaiojus custom viewing. Yeah, this one. Oh, there's a tab open somewhere with it. And this pull request. So this is going to be here. This is going to be here. And I shall add this to the description of the video in the code we're working on. And then let's now finish our notes as well. So let's finish our notes. Let's close that because we don't need that. Let's finish our notes. So this is cool. This is cool. This is cool. This enables us to account for active audio and background noise. Okay, cool. So and then let's go here. Let's copy this and use this as the. Okay, let's copy that and use that as the description of the video because that's actually what happens. Copy. Copy. Okay, cool. I need to edit it on YouTube a bit so that it's cleaner to use. Yeah, if anyone has any more questions right now, it would be nice to ask because then I'm just doing this admin and we're done with the stream and this is amazing. But I am finally glad we managed to get the root mean square of this signal that has been evading us for so long. Okay, and I see manageable is a thing here. I could do that. Git status, git add 2025 or 9. Cool. Git commit -n add audio decoding blog notes. Git push, that should be there. That should go. Cool. That should come to gayaochos.com. gayaochos.com. Okay. So I keep a set of notes. For everything I'm doing. And that's gonna come here just in a second. I don't think I'm going to wait for it to deploy, but this is going to be added as a link on YouTube. And then that's it for today. Thank you guys so much, and gals, for hanging out with me today. That was the beginning of us processing our audio signal and actually consuming it in something that we can use. So thank you so much for coming. I'll see you guys tomorrow on the stream, and that should be it for today. That was fun. That was a lot of fun hanging out. And thank you so much, Shashank, for all your questions and for hanging out and the curiosities. And yeah, thank you. Cheers, everyone. Bye.